Today we shall discuss different techniques and methodologies to be followed for developing embedded systems. We have looked at the design process. We have also looked at some of the features that is required in compilers to generate efficient code for embedded systems. Today we shall continue with the discussion in terms of architecture specific features of compilers and then the subsequent steps and methods to be followed for development of embedded systems. So, in the last class we had discussed retargetable compilers. We had also referred to the cases where we need to have more architecture specific features for compilers, particularly say for digital signal processors, VLIW processors as well as for multimedia data processing. In today's class we shall see how compilers explore those features. The first thing is compilation for DSPs. In fact, digital signal processors have got various spatial features which distinguish them from a general purpose microcontroller. When a compiler is being designed to generate code for such digital signal processors, it has to take care of these specific and spatial features. There will be spatial instructions and these spatial instructions have to be selected for generation of the code. The most common spatial instruction is your multiply and accumulate MLA instruction, and use of ML instructions have to be judiciously made. Another interesting feature is address generation schemes. Many of these DSPs provide support for auto increment and auto decrement operations. In fact, your general purpose processor like ARM also provides this feature. In fact, ARM in various ways do incorporate DSP features. Then there is support for loop. In fact, what is called as zero overhead loop, that support is there in the hardware, and compiler therefore should exploit these spatial features. We shall see how these spatial features can be really exploited. Let us take an example of an architecture. This is a DSP processor, and typically say you will be working out these kind of computations. If you consider these as a data stream, what you are doing is you are basically multiplying by a coefficient and getting the result as summation, and this is an incremental addition of the sum. So, if we can put it together, so I am basically generating a stream of y values which is dependent on the previous y value as well as input stream. So, these are very typical computations which you encounter for a signal processing task. And the architecture typically supports various registers. So, for example, here what we had seen is that I have got AI, I have got xj minus I, and they will be computed and we shall get yi minus 1, which have to be used for the subsequent steps as well. So, how to use these registers optimally, that becomes a basic problem. Okay? And you also have automatic address generation units. Now, you have to use automatic address generation units so that you can generate addresses for this kind of sequential access. Okay? So, what we say that there is a parallelism inbuilt into it, there are dedicated registers. So, if I cannot match these requirements with that of the compiler's basic code generation scheme, then in no way I can generate efficient code. So, basic problem is that of matching. In fact, we shall look at this problem in the context of a simpler example, okay? Because if you look at the problem in its complete complexity, it is really complicated, and there has been various sophisticated techniques developed for generation of codes taking into account these considerations. We shall consider a simpler problem, that of addressing variables. Let us say we have got variables a, b, c, d. stored in consecutive memory locations, okay, and which are accessed in a sequence B, D, A, C, D, C depending on the computation. Okay. It is not a strictly sequential access, but we are accessing them B, D, A, C, D, C. So, I am not accessing them A, B, C, D, but in a different order, although these variables can be typically stored in the memory A, B, C, D. And in majority of the cases, you will be accessing these variables using register indirect addressing. The question is there an optimal layout of these variables so that I can use auto increment or auto decrement option of the processor in an optimal fashion. Okay. So, what we see is that a number of address calculation operations are required if we assume a single address register A. In fact, you can understand this is a kind of an abstraction. We are looking at the simplified version of the problem to understand its complexity and the way in which it can be tackled. So, a number of address calculation operations are required if we assume a single address register, and auto increment or auto decrement cannot take care of access requirements, okay. Simply because after A, it is not that you are accessing B, because B is placed after A. You are first accessing B and then you are accessing D, and if they are placed even in consecutive locations, what is interesting to note is that I may load initially address of B into my address register, indirect address register, but by incrementing it by 1 will not take me to D. So, I have to do actually an arithmetic operation on that address register and to access D. So, that means I have to execute a separate instruction. If I could have used auto increment, that means I do not need a special instruction to do address calculation. If I do not use a special instruction for address calculation, it means I consume less time, I consume less energy. So, if the layout now changes to BDCA, okay, so what is interesting you can see is that I can do A plus plus, then I increment A by 2, fine, this is required, and then I can decrement and again I can increment. In fact, most of these address calculation operations are executed in parallel with some operation in the data path, because auto increment and auto decrement feature is part of your address generation unit. So, let us pictorially look at what we are talking about. Say this is my variables A, B, C, D. So, I have these variables A, B, C, D, they are stored in consecutive locations. This is an assumption. I have got a single address register AR through which I am accessing these variables. So, if I load first, if I have to access B, I have to load 1. If I am loading 1, that means I have got my address of B here with the register AR. So, I can load the content of B. Now, next I need to access D. So, I have to increase AR by 2, because then only I can go to D. After D, I want to access A. So, I have to decrement AR by 3. Again I have to increment AR by 2. So, all these operations are actually involved. Okay. So, these all consume time. Now, when I change my layout to say B, D, C, A, just look at this layout. What is happening here? The basic issue here is that I am loading AR0, and then if I increment by 1, I go to D. For going to A, I need to increment by 2, no doubt about it, but subsequently it is all either decrement by a single value to go to C, decrement by again a single value to go to D, and then you increment it, okay, to again come to C. So, here then all these operations AR, decrementations as well as incrementation will take place in parallel using the address generation unit. So, you can see this layout is more efficient. In fact, a compiler's problem is therefore to exploit auto increment and auto decrement features of the instruction set is that of figuring out an optimal layout of these variables. Okay. The variables, depending on their access pattern, compiler should decide about its layout. Okay. Compiler cannot use as such a kind of an predetermined fixed layout for storing these variables. If it is doing so, then it is paying for in terms of additional instructions. So, how to do that? So, you consider what is called a variable access graph. There are various techniques. We shall just consider one such technique, a very simple technique which can be understood. So, we consider a very simple access graph, okay. And in that access graph, if you find that there are variables A, B, C, D, and there are links between the variables indicating adjacent access. Now, this is not 11, this is 1, okay. So, A is connected to C by a link because A and C has got an adjacent access, and there is only one adjacent access for the problem that we have considered. So, the link weight is 1, okay. C and D has got 2 adjacent accesses, okay. So, that is why the link weight is 2. A and D has got 1 adjacent access, B and D has got 1 adjacent access. So, therefore, I have got a graph. In the graph, the links indicate whether there are adjacent access of these variables, and the weight of the link indicates the number of times this kind of adjacent access takes place. Number of times this kind of adjacent access takes place. Now, from this graph, I can extract out what we call maximum linear path. In fact, this is the maximum linear path. So, what does that mean? That means, if you look at these variables, this is the path along which the maximal accesses take place, okay. Because if we add up this one single path, okay, this path gives you the kind of accesses that is there, okay. There may be more than one such linear path also, but here the interesting thing is what we have figured out here is that this gives you a linear path connecting all the variables depending on their access pattern. And what it is suggesting, that if I now put A, C, D, B, that is C and D are consecutive, that would maximally exploit the auto increment decrement operations because that weight is maximum, okay. Similarly, A and C should be put together because there is an adjacent access, and there is no reason for putting A and B together at consecutive locations because there is no adjacent access between A and B, okay. And D and B, there is an adjacent access, so there is a reason for trying to put them in a adjacent location, okay. So, the basic problem is that of figuring out the maximum linear path. In fact, this is purely a graph theoretic problem. So, what we say is that variables connected by links of high weight should be allocated to adjacent memory locations. I think intuitively the reason for it is clear, because that gives you the number of maximum adjacent locations, and then only I can use auto increment and auto decrement features to the maximum possible extent. So, number of address calculations saved is proportional to the weight of corresponding weight, and the goal is therefore to find a linear path of maximum weight, so that linear ordering of variables in memory maximizes use of auto increment or auto decrement operations. In fact, again I have mapped the problem to an optimization problem, because I can have a variable access graph, and in the variable access graph I have to find out the linear path of maximum weight, and the linear path of maximum weight will decide on the layout of the variables. I am not going into the exact algorithm to be used for solving this optimization problem, but you should understand that if I can solve this optimization problem, I shall get the optimal layout of the variables. Obviously, with the assumption here is what, that I am using one address register for register indirect addressing. If I talk about using more than one registers, talk about using automatic address generation unit, the problem becomes more complex. Next, we shall look at multimedia processors. In fact, majority of the multimedia processors use what are called today use packed data types. In fact, we have looked at packed data types in the context of Pentium processors also with MMX enhanced instructions, where I can pack multiple bytes or multiple integers together into a single word and use a single instruction to operate in parallel on the multiple data elements packed into one word. Okay, that means if I pack 8 bytes together in a 64-bit word, and if we are using any of these multimedia instructions, I carry out an arithmetic operation in parallel on those 8 bytes. So, I am having a kind of a parallelism exploiting just the ALU feature for a 64-bit word. And what is the advantage here in this case? In this case, the advantage is in many of this multimedia processing, you need to use same operation repeatedly on a number of data items. So, I am actually having a kind of an instruction set which is supporting what we call single instruction multiple data parallelism. Okay. Now, the compiler's job is to figure out that parallelism, because when you write a processing operation, okay, in a high level code, say you want to add a fixed value to each pixel in an image. Okay. So, an image is what? A 2D array, and if you are adding a single value, okay, to each of the pixel, you will be writing a nested for loop. The compiler needs to figure out from the nested for loop, okay, the operations, so that it can be converted into a packed operation and a packed data type. This is the basic problem. So, what we say that in order to support packed data type, compilers must be able to automatically convert operations in loops to operations on packed data types. So, the operation that I am doing on 256 cross 256 pixels individually have to be converted into appropriate number of times in the loop, because I can now pack 8 pixels of 8 bits together into a single packed data type and use a single operation maybe to increment each of those bytes. Now, combination of these with zero overhead loop can provide a significant speed up. So, that is the basic issue, that compilers need to know that there is a packed data type. It has the ability to identify the loops corresponding to which the packed data types can be really used. It is not that it can be used for any for loop for that matter. So, it should analyze the code, have the ability to analyze the code and use the packed data types. When you look at VLIW processors, it requires some amount of spatial optimizations, because there are multiple functional units, okay, and these multiple functional units can carry out independent operations. So, the compiler's task is to allocate individual computational jobs to functional units as well as to the corresponding register paths, okay, because the registers, if you remember the VLIW architecture, registers are linked to various functional units, and there are different kind of register organizations which is adopted by VLIW processors for connecting the registers to the functional units. So, a very interesting and important problem of the compiler to optimally decide on usage of these registers, on the usage of these registers, so that the functional units can be exploited. So, it is no point using a VLIW processor and carrying out only one computational job in an instruction, because in that case your functional units are remaining idle. So, the point therefore comes back to is that you look at the computation as a whole. The problem is that of partitioning of computation into multiple paths of execution, and these paths of executions have to be mapped to the set of registers and the corresponding functional units, okay. And these paths, in a way, we have to identify such that their dependencies are minimum. If they have got dependencies, then I cannot schedule operations in parallel. So, these dependencies have to be figured out. You have to apply operations to minimize the dependencies or to eliminate the dependencies, then identify the different execution paths and map the different execution paths on the registers and the functional units, so that the potential of the processor can be completely exploited. In fact, related to this is what is called branch delay penalty. Why branch delay penalty is critical for VLIW processor? Because if there is a branching, then what are the operations scheduled, okay, on different functional units may go haywire, because that may not be required at all. In that case, a branch will cause a kind of a penalty, okay, a delay, effectively a delay. So, branch delay penalty for VLIW processors is something which is very important. In fact, it is true also for pipeline processors. Okay, there also the instruction scheduling has to be such that pipeline should not be empty or has to be flashed at a regular interval. So, one way to deal with this problem is, you know, predicated execution to efficiently implemented small if statements. What is a predicated execution? It is nothing but conditional execution. Okay, depending on some predicate, that is some condition, you execute instructions. In fact, we have seen such instructions in ARM processor as well. Okay, so if I use conditional instructions, what happens? My pipeline need not be flushed. Effectively, I am getting a NOP inserted if that condition is not satisfied and the corresponding operation is not really getting executed, but the pipeline need not be flushed. Similarly, for VLIW processors, the scheduling of instructions as such, okay, that this schedule need not be changed because of this problem. Okay, so what we say that predicated in execution to efficiently implement small if statements. Okay, so I should use conditional instructions to implement small if. I should not make a conditional jump. The moment I am making a conditional jump, the entire set of instructions which are to be executed has to be changed, and that introduces overhead, that introduces branch delay penalty, which should be avoided. In fact, in this context, inlining is also useful. What is inlining? In fact, whenever there is a function call, there is similar penalty, just like a branch delay penalty. Whenever there is a function call, there will be a similar penalty. Okay. Now, the question is, if the function is small enough, you should not call that function. If the function is small enough, you should not call that function. You insert the code of that function at an appropriate position where it has been called. Obviously, you can realize the moment I do inlining, the memory requirement of the code increases, but the efficiency of its execution at the same time is better off. In fact, inlining is a universal technique. In various cases, even if you are not using a VLIW processors, compilers do resort to inlining. Whenever there is a small function calls, it may decide for the purpose of optimizing the code to replace the function call by the actual code itself, because you then save the overhead of saving the registers, pushing the current program counter, and again when you are returning from the call, you have the overhead of popping the registers as well as getting the address from the stack. So, those overheads are completely avoided if I do inlining. So, compilers as part of generic optimization strategy also use inlining. But in the context of VLIW processors, this becomes more important, because you have now got multiple functional units, and multiple functional units idling away because of a call for a small function is potentially more problematic than wasting away few instruction cycles in a non-VLIW processors. Okay. So, that is the precisely reason why inlining is extremely useful for VLIW processors. So, this more or less covers our basic techniques that we had so far talked about for the compilers for embedded systems and architecture specific features, and you must have realized by now that compilers also therefore become a very important tool in the complete design process, because without the help of a good compiler, you cannot generate efficient code. If you cannot generate efficient code, the question of performance estimation in terms of your time as well as energy computations, okay, is no longer very useful. Because if you are using an inefficient compiler, generating inefficient code, doing a performance estimate and finding that you cannot meet the requirements and therefore go for a better processor, then you are not actually exploiting the potential of the processor. And that is why compiler is a critical tool for doing an embedded system design. So, once we have done the design or working with it, we should also know that what are the variants of these compilers that are also today used in various embedded systems. In fact, interpreters and just-in-time compilers are two variants of classical compilers which is found very commonly today in embedded systems. This is particularly true in the context of Java enabled embedded systems. Okay. If we have seen that today, in order to provide a flexible programmability to the embedded systems, we have what we call Java virtual machine built into an embedded system. So, what does a Java virtual machine do? A Java virtual machine typically interprets what is called Java bytecode, and Java bytecode is obtained by compiling the Java source code. Okay. What is really interpretation? Interpretation is translation and execution of program statements on the fly. In a very simplified fashion, you can consider that there is a single statement, okay, that is Java bytecode, and that statement is being translated to the machine code of the target processor. In fact, Java bytecode will be in a language of Java virtual machine. That means it would use the instruction set of Java virtual machine, and you might be actually running your application on, say, an ARM processor. So, each instruction of Java virtual machine needs to be now translated to a machine instruction of the target processor. Interpreter actually does that job. Okay. In fact, Java virtual machine in a way is that interpreter. So, what it does? It translates instructions one after another. Now, what is the advantage or drawback of this? Advantage is very straightforward. I can download the Java code from any source, okay, because I do not need to have the Java code translated to the machine instruction of my processor. I can get universal bytecode, load it onto my appliance and execute on my appliance. So, that is the advantage of the interpretative scheme. What is the disadvantage? Disadvantage is the kind of optimizations that I had talked about for the compilers, it is not possible to be applied there, because you are not looking at a set of instructions, but considering instructions individually. So, interpreters really cannot implement the kind of optimizations that we have talked about. But optimizations are critically important if we are interested in running Java on embedded systems, because we have understood that from the examples and the issues that we have examined. So, there is now a concept, okay. In fact, in terms of architecture of the compiler, we have a concept what is called just-in-time compiler. So, what does a just-in-time compiler does? Just-in-time compiler, put in a very simplified way, is something in between a full-fledged compiler and an interpreter. Just-in-time compiler will look at not at the complete code, but maybe at section of the code, okay, and it would now compile that section of the code into the machine instructions of the target processor. Okay. So, in this case what happens? The compiler, the just-in-time compiler has the option to carry out optimization with respect to a small section of the code, may not be the complete section of the code, but at least a small section of the code, and hence you can actually generate optimized code and not non-optimized code which results if I look at instructions individually for say a Java bytecode. And since it is looking at small part of the code and looking at a small part of the bytecode, actually lots of translation overheads are in a way eliminated. Okay? So, you need not bother to maintain a complex symbol table and those kind of data structures as it is required for a complex and a complete compiler. But obviously, it would require more memory. Why more memory? Because it has to now deal with a section of the code together and then convert that code through processing into the target machine code. In the earlier case, interpreter can just look at in a very abstract scenario, the interpreter can look at a single instruction and convert that to a machine code. So, it did not have a memory to keep track of a section of the code, putting it through a set of transformations for the possible optimized target code to be generated. So, in fact, just-in-time compilation techniques are very useful, particularly for implementation of optimized Java code in embedded systems. So, once we have got therefore tools to do hardware software partitioning, then hardware design, we have looked at hardware design in terms of processor choice or specification of the computation. Also, we have looked at software design, translation to the architecture specific instructions. So, we have all the design tools with us and we can do the design. Next question comes that of design and product validation, okay? Because we had started with what? We had started with a requirement specification. The requirements could be functional as well as non-functional. Once we have done the design, we now need to know whether at the end of the day I am meeting my requirement specifications or not. So, validation is a process of checking whether or not a certain design is appropriate for its purpose, meets all constraints and will perform as expected. So, this is basically what is known as validation. Now, validation can be done in a very formal way. So, validation with mathematical rigor is called formal validation. But formally verified tools, what they do? They transform specifications into implementations, and in that case you have got correctness by constructions. That means, if you are using tools which are formally verified, that means tools are guaranteed to generate designs which are to be correct, then you get a correct design through construction, provided you have given the tool correct specifications. If your specification itself is wrong, you cannot get an implementation which would be correct. You will get an implementation which is correct with respect to your specification. But in practice, in majority of the cases, you usually do not use this kind of formally verified tools and you go through manual design steps. You might be using tools at various steps, but the overall design obviously involves manual interventions and manual decisions. So, in that case, validation of each and every design is required, and unfortunately it has to be done at intermediate state and not just for the final design, because if you are waiting till the final design, then the man months and the money spent for doing that goes waste. So, how it is done? A very simple way is simulations, because simulations try to imitate behavior of the real system on a digital computer. Simulation of the functional behavior requires what we call executable models, okay? Because I need to know how to execute the whole system. And simulations can be performed at various levels. In fact, we had talked about behavioral simulation just to see whether the behavior is being met. At a second level, I can do a clock level simulation to see whether the timing constraints can be actually met. And we can do these therefore simulation at various levels, and you can do hardware and software co-simulation as well. That means we can design the architecture, map the architecture to a simulated test bed, have the code and run the code while simulating the architecture on the simulation test bed. In fact, some non-functional properties, example temperatures, EMC, can also be simulated. So, EMC is basically electromagnetic conditions which are there prevailing in the environment in which your embedded system is expected to be placed. So, simulations are typically slower than actual design, and violations of timing constraints likely if simulator is connected to the actual environment. Okay, because simulation obviously means you are doing some kind of approximations, number one. Number two is you are also doing, to monitor the performance, some kind of management of the environment, that code which goes into management of the environment, that is housekeeping tasks, that itself can consume time, and so it is typically slower than actual design. Next thing is simulations in the real environment can be dangerous. Obviously, you won't like to simulate a safety critical system with a real object. So, you won't like simulations to produce catastrophic results. And there may be huge amounts of data, and it may be impossible to simulate enough data in the available time. See, if I am actually designing a compression engine, then I have to actually get a volume of data to verify whether the compression engine is working correctly or not. And most actual systems are too complex to allow simulating all possible cases, okay? Because then the time requirement for doing the simulation becomes high. So, simulations are done typically at an intermediate stage, and simulations can help us to find errors in our designs, but they cannot guarantee absence of errors. Okay? This is the very basic observation. Simulations can help us to find errors in our designs, but they cannot really guarantee a complete absence of errors. In fact, we need to develop prototypes after we have gone through the simulation in order to have some assessment about the quality and the nature of the product. So, what we come to is rapid prototyping. Okay? So, embedded system, a prototype is what? A prototype is an embedded system that can be generated quickly and behaves very similar to the final product. Okay? Maybe larger. So, when we are talking about a prototype, we may relax some of the performance constraints, some of the non-functional constraints in order to do the rapid prototyping. So, that means we can have maybe physical size wise a larger system. We may have a system which is more power consuming and have other properties that can be accepted in the validation phase. In fact, typically what happens in for an auto industry, the practiced way to validate design of an embedded system targeted for auto industry is to build prototypes. Okay? The prototypes may not exactly fit into all your engineering aspects of the design. That means, say for example, if you are trying to design a navigation aid which is likely to go into your dashboard, you might not really design a product meeting the measurements, weight, as well as battery power consumption requirements. You might build a system, okay, which may not have these constraints, but verify whether it is providing the navigation. If it is providing the navigation, the next part of the engineering aspect of the design is reducing its size, try to optimize for the power, etc. And many cases, these prototypes are built using FPGAs, because FPGAs can be very easily synthesized starting from say VHDL or System C descriptions of the embedded appliance. So, from there we can build FPGAs, we can even execute our code on these prototypes, FPGA based prototypes, and verify the overall design. Once that overall design is verified, now these FPGAs can be converted to an ASIC or SoC as the case may be. In fact, you can have even FPGAs with processors. Okay, we have looked at such platforms. If we really have such platforms, okay, then what we can do? We can use such platforms also for design validation. May not be final design, but also for design validation. So, next thing is testing. Okay. So, in fact, a validation process really involves testing. So, test patterns are applied to real already manufactured systems. In fact, when we build a prototype, there also we have to apply the test patterns to check whether it is meeting our requirements or not. But typically test refers to what we call manufacturing test and field test. That means, if we assume that we have gone through a design validation process, we have finally designed the product and we are in the process of getting the product out, then products have also to be tested. Okay. So, there are two kinds of tests that products typically undergo. One is called manufacturing test, the other is field test. The purpose of the manufacturing test is to identify systems that have not been correctly manufactured, and field test to identify systems that fail later. It may be so that we may not apply, strictly speaking, manufacturing test to each and every appliance or each and every product that I am manufacturing. In fact, there are typical what are called statistical quality control standards and paradigms which are followed for the purpose of sampling out the products and testing them out. If from a batch of products we find that the number of products turning out to be failed or fault prone or failure prone is that such number is greater than a threshold as per SQC norms, then we might need to reject the complete batch of products. If we find such faulty cases as less than threshold, we may accept the entire batch. Okay. So, the testing involves test pattern generation, test pattern application, response observation and result comparison. Okay. So, I need to apply a test pattern, okay, need to generate the test pattern, then apply the test pattern, see what kind of observation the system is providing and figure out whether the result that you are getting meets your specification or not. Test pattern generation typically considers certain fault models, because you have to have the fault models without which you cannot really generate the test patterns. So, what does that mean? It generates patterns that enable a distinction between a faulty and a fault free case. So, what are different kinds of fault models? Typically, we are looking at hardware fault models. Hardware fault models can be stuck at fault model. Each and every net can be permanently connected to the ground or VDD. That means, each and every line can be connected to VDD or ground. So, you can test out, if I look at stuck at fault model, you can always figure out an input data combination which would give you an incorrect output if a particular say data path in a processor is stuck at 0 or stuck at 1. Similar thing would be true if any data line or an address line for a memory chip is stuck at 0 or stuck at 1. The other thing is stuck open faults, that open transistors can behave like memories, CMOS devices. So, in fact, stuck open means there are disconnections. So, you need to know what kind of behavior is expected of the device, and accordingly you have to decide on the test data, so that you can figure out whether such an error has occurred or not. Also, there are delay faults. There may be cases in which the circuitry is functionally correct, but delay is not. Okay. Because delay in a circuit can be, say if I look at a very sequential circuit, it would depend on the number of gates, okay, that is there in a path. So, propagation delay would give you the actual switching delay. Now, you might have got a design where propagation delay is such that you are getting a switching delay which exceeds the constraints, but functionally the circuit is behaving the way you would like to. Okay. So, you got to have testing strategy, so that these delay faults can be identified. Related to this is a concept of what is called fault coverage. A certain set of test patterns will not always detect all faults that are possible within a fault model, because that is not really always possible. Then the number of test patterns that you need to use can become very large. Okay. So, we have to select a set of test patterns which will detect the different faults as suggested by the corresponding fault model. Now, to actually evaluate the tests, we use a parameter which is called fault coverage. Fault coverage is the number of detectable faults for a given test pattern divided by the number of faults possible due to fault model. Okay. So, coverage if is 1, if we have tested with all possible test patterns, then in that case I can cover all possible models, all possible faults that can be there because of a particular fault model. But if for the purpose of efficiency, we would like to use a coverage which may be as close to 1, but may not be really 1. And our objective would be select a set of test patterns. The set of test patterns may be small enough and give high coverage. Now, similar testing has to be carried out for the software as well, okay? Because software is a driving force behind the hardware. Okay? We can check the hardware circuitry, but when and how to use the hardware circuitry would be determined by the software running in the embedded system. So, testing of the software for embedded systems is also critically important. So, basic testing procedure: provide the program with inputs, execute the program and compare the outputs to expected results. That is the standard is same as that of the hardware. What are the types of software testing you really have? Black box testing and clear box testing, and these are very in fact standard software engineering practices have to be followed here as well. In a black box test, tests are generated without the knowledge of program internals. In fact, these tests are typically generated from the specifications. That means, once you know the functional specification, given the functional specification, you should design the black box tests. Because if you try to design the tests by knowing how it has been implemented, then you may miss out certain aspects of the specification altogether. The other thing is clear box testing. Tests are generated from the program structure. In fact, typically you would be doing a clear box testing first and then go into a kind of black box testing. What is a clear box testing? It generates tests based on structure of the program. So, the question is a given block of code executed when we think it should be executed, okay? Or that means, is my control path correct? Does a variable receive the value we think it should get? That means, the computation assignment process is correct or not. And one aspect or one way of doing clear box testing is what is called path based testing. In fact, clear box testing obviously cannot test all possible paths in the program. It would select and test few of the possible paths. So, use a control program to exercise a path. You observe the program to determine if path was properly executed or not, and may look at whether location on path was reached. So, this is a control aspect of it, and whether variable on data path was set. This is the data aspect of it. So, typically in a clear box testing, you do what is known as path based testing. So, your problem is that of choosing the paths, okay? Fine. In a hardware, it was the problem of choosing the test patterns, okay, such that you have the maximum fault coverage. In case of software, if you are doing a clear box path, the problem is that of choosing paths, and once you choose the path, then only the problem of test pattern will come in, because test pattern or test input will force the software to go through these paths. So, there can be two possible criteria for selecting paths: execute every statement at least once and execute every direction of a branch at least once. Okay. This is equivalent, both of these, for structured programs, but not for programs with gotos. Okay. In many cases for embedded systems, you really write programs with gotos. A very simple example we have seen in the last class, that when we are using scratchpad memory, I have to put goto for a set of code which is put in scratchpad memory and come back. Okay. So, I need to have tests to check whether those gotos are also taking place correctly or not. So, execute every statement at least once and execute every direction of a branch at least once. So, take an example. This is a simple flow graph. In fact, this is a representation of the program as a CDFG. So, if I take a path, so if I take these two paths, it covers all statements. Okay, it covers all statements, but it does not cover this branch. Okay. So, I need to check these as well, condition as well, to test all branches corresponding to this CDFG. Now, for testing the branch, we have to exercise elements of a conditional statement, but not just one and one false case, because there are various combinations can really come up. So, take an example. Let us say I have target statement is if A or B is greater than C. This is the condition I would like to execute. This is a branch statement, okay. And the very common mistake is this, okay. Very common mistake is this. Now, if we use a test, and this test is important because you have to select the test data such that these two can be distinguished, because you do not know where in the code such an error has crept in, and you need to figure out exactly the data combination, so that if there are such errors, branch testing error, it should be possible to identify, because there may be combination of inputs where for both the cases you get the same result. Then it is not possible to figure out that this is an error which is there, and this is a very common error for of the branch statements. Another example is this, a pointer related error. This is an assignment, okay, and this is an equality. So, if you have this assignment, the entire thing will go haywire, fine. And here also if you simply check that is what I said, that if you only check the field value, then both the cases will give me identical results, and this whole error will remain undetected. So, these errors are very critical errors. They can be they are really problematic, okay. So, your branch testing becomes, that is why, important. Then other thing is domain testing, when you really use inequalities. So, typically what we say, test two cases on boundary and one on outside the boundary, because if I have an example that less than equal to I plus 1, then I need to do the test on the boundary, because there can be various values of j and I, and this is really defining a partition. So, the question is, by putting in values of j and I should check whether I am really at the boundary or I am outside the boundary or inside the boundary. So, a thumb rule says that you should test two cases on boundary and one outside the boundary. This is domain testing. I am just giving you the basic flavor of domain testing. Domain testing means that whenever such inequalities are there, corresponding to the inequalities, you have to make a choice of your test patterns. So, if you look at the branch testing, domain testing, we went into that from the perspective of finding out the paths to be covered. And these testing schemes actually provide you with the exact nature of test patterns which is to be used. Data flow testing is this, say if I am defining a variable, am I using the variable correctly, okay. Then there are loop testing. The loop is, various conditions can happen with the loop. You would like to skip the loop entirely. You would like to go through one iterations, multiple iterations, look at mid-range properties and look at boundary. N minus 1, if n is the boundary for a loop, n minus 1, n and n plus 1 iterations. Is it really the loop is going through n plus 1? That means there is an error if n is a boundary. The black box testing, I said that made from specifications and not from the code, and complements clear box, and typically should test unusual cases better. In fact, ideally a person who is designing a black box test for an appliance should not know how it has been implemented. He should only know its complete specification, and in fact black box testing can also unearth actually gaps in the specification. There can be missing points in the specifications. So, black box testing can unearth such gaps as well. So, there are various kinds of black box testing, specified input outputs. So, select input from specifications and determine the required outputs from specification and see whether it matches. There can be random, generate random tests and determine appropriate output. And there can be tests used in previous versions of the system. If you are generating a new version, it should be consistent with previous versions. How do you evaluate tests? You evaluate tests by keeping track of the bugs, okay? But it is not always possible to know whether you have taken care of all possible conditions. So, what do? You inject bugs. So, the basic idea is the injection of the bugs, and two types of fault injection is there: local faults within the system and faults in the environment. Okay. We can check when we have talking about faults in the environment, we can check how the system behaves if it is operated outside the specified temperature or radiation changes. Okay. Typical hardware fault injection would mean signal manipulation at the pin. So, that means what I am doing? I have designed a system, now I am trying to inject fault into the system. You can manipulate signals at the pin, okay. You can apply electromagnetic field or nuclear radiation and see, these are all hardware kind of fault injections, and see how the system behaves. Then for fault, software fault injections, you can actually modify the code, introduce bug or modify the data. So, advantage is its predictability. It is possible to reproduce every injected fault in time and space, because you know what the fault you are introducing, and you can reach storage locations within chips instead of just pins, because this is not possible if you are using only hardware manipulating the signals and not really the software code, and it is of less effort than physical fault injection. So, software fault injection with bit flips in the data is comparable to hardware fault injection. So, if you see typically like Stockett faults would give you what? Bit flips. So, I can flip that data in the memory and see whether the system is working correctly or not, what is the behavior, whether it can be taken care of or not. And at an application level, the software error detection is higher. So, one way of testing is what we have talked about is we have defined the testing schemes, we have defined the test patterns, and to see whether your system gives a desirable behavior, you inject fault into the system, because you cannot really expect the faults or the bugs to come up on your own always, and see that if you inject a fault, whether that fault is getting detected by your testing process or not, because you exactly know the fault that has been introduced, and then you can be sure that your testing process is correct and your implementation is possibly desirable. There are also formal ways of doing it. The formal verification is concerned with absolutely rigorous mathematical techniques. You can use formal logic, maybe propositional logic, first order logic or higher order logic to verify the system. And in this case what happens? You build a formal mathematical model of the system. That is a manual effort. And with respect to the mathematical model, try to prove certain properties. If such properties are proven, then you can say that your system is guaranteed to show that kind of a behavior. In fact, I had talked about the formal construction tools, okay, when I talked about validation. Okay. So, a construction tools would obviously implies that they are incorporating this kind of formal verification schemes as well. So, what we have looked at today at different features of architecture specific compilers and studied the different system development phases, validation, testing and verification.